led by the youngest professor in the world, Suborno Isaac Barry.
You can see light energy as an energy function. This energy function behaves in such a way that you minimize the energy spent on traveling.
Oh, so as is minimizing the distance?
Yep. Just like minimizing the distance, it minimizes the energy.
Well, yeah. The energy taken away, I guess, in a metaphorical way, because light's energy, I guess, stays constant. I guess the path takes the least time. So yeah, that probably does have something to do with optimization that I could explore.
Probability half to the coordinate 0, 1. The coordinate 0, 1 is on the y-axis.
Yes.
Okay. With probability half, it bounces. With probability half, it remains there. That means you toss a coin. If you get heads, the particle goes to 1, the point 0, 1. If it comes tails, it remains there only.
Okay, so
okay.
There's a 1/2 chance for it to move up and a 1/2 chance for it to remain
Stay
stable.
there, right? You do it sequentially for a long time.
Okay.
Ultimately, what is the behavior of the particle?
Well, sometimes it will move up and sometimes it will stay there. So eventually, it will just keep moving up, because if there's no way for it to move down, then its y-coordinate will approach infinity as time approaches infinity.
As time approaches infinity,
its y-coordinate is going to approach infinity as well, because there's no way for it to move down, and there's a 1/2 chance for it to move up. So at some point,
at some point,
yeah,
okay.
So it will keep moving up and up.
Okay, but it can never go down.
Yes, so that means that its y-coordinate will approach infinity. If there's a 1/2 chance for it to go up and a 1/2 chance for it to go down, its y-coordinate will probably approach 0.
What is the name given to this problem?
I have not heard of it before, so
Well, that's the first time you heard of it.
yes. What is the three-body problem?
Let's say there are 3 bodies, planetary system. There are 3 masses, huge masses.
Yes.
They are interacting with each other. Like, for
Okay.
example, Earth, Mars, and Jupiter. Imagine no other bodies are there, only Earth, Mars, and Jupiter.
So they're interacting with each other through gravitation.
Because of gravity.
Okay.
So, will there be an equilibrium?
Well, I'd have to draw it out in order to see.
Right?
Let me try it. So, if I have 3 masses, can I assume they're like equal mass or?
Okay.
Okay. So if I assume they're like equal mass or something, the attraction to this one is going to be Gm squared over r squared. So let's just say this is an equilateral triangle. Gm squared over r squared. Here, the attraction is also Gm squared over r squared. So it's like a love triangle. So we have these 2 attractions, these 2 attractions, and these 2 attractions. So if we're asking if all these forces sum up to 0, they have to, right? Well, no, actually, these 2 are going to collapse towards each other. These 2 are going to collapse towards each other. These 2 are going to collapse towards each other.
Yes.
That seems correct to me. Over here, will it collapse here or will it collapse there? And then, yeah, and this is considering the simplest case where they have.
Supposing, okay, let's see. Supposing this is moving, this is pulling it this side.
Yes.
So it is constrained. Its motion is constrained by this guy.
So, oh goodness, can we like break this into 2 different components? I guess. So for example, if we have theta, then we have gm over r squared cosine theta, and then gm over r squared sine theta. Gm squared over r squared sine theta. And then we have gm squared over r squared times 1 minus cosine theta. And then that means it depends on theta between all of these, which I guess I can assume to be 60. If we're assuming the radii are all equal. Over 2r squared is going to be the attraction this way. So, wait, no, they're gonna sum up. Okay, yeah. So it's this way and that way, so 1 plus 1.5. So 3gm squared over 2. Okay, so that means it's going to be attracted this way with 3gm squared over 2r squared, and this way with gm squared over r squared. Sine 60 is root 3 over 2. Sum those up in some way, so you have this, 3, this, so it's going to be attracted that way. That's disturbing. This way it's going to act the same, and this way, well, these two are going to sum together. This is gm squared over r squared. How can we find theta? Oh wait, no, this, yeah, okay. So theta here is going to be 30, I guess. So gm squared over r squared cosine 30 times 2. That's what this is going to look like. Okay. How do we express this? Huh? Oh. Oh, thank you. Okay. So gm squared root 3 over r squared is going to be how it looks downward. And then this way and that way, they're going to cancel out. So that means we have this way, that way, and that way. They're all going to converge in the center. Of course, that's assuming they're all the same mass and they're all the same distance away from each other. But they seem to all converge in the center for this case.
Correct.